let's talk a little bit about classical walks versus quantum walks. So we've all read in our statistical mechanical courses about classical walk, where there's a classical random walker who does a classical coin toss, and based on that, he either goes to the left or the right position with some finite probabilities, and there's a certain path that the walker can take based on the outcome of the coin toss. But in quantum walk, what happens is that because of superposition, as well as because of interference, a quantum walker can actually take multiple paths at the same time. And because of this, there can be multiple trajectories, and all of these trajectories can actually interfere with each other and create some interesting dynamics. Now, just for the sake of consistency, I would like to talk a little bit about waveguides. We all know that a waveguide is a particular system which uses a set of coherent cladding having different refractive indices, and because of this, light is guided inside the waveguides using total internal reflection. Now, what I would like you to know is that the intensity of light, classical light that travels inside waveguides, is actually having a Gaussian permittivity profile. So you can see over here that this intensity distribution is actually Gaussian in nature. So what happens when we keep two waveguides very close to each other? If we keep two waveguides in very close physical proximity, very close in physical space, something about the distance of 40 times the wavelength of the light, which is traveling inside, then what happens is we observe that over time, because there's a Gaussian intensity profile, suppose I launch a single photon into a waveguide number 1. What I will observe is that the probability distribution of the photons, the spatial probability distribution of the photon, is also Gaussian. And since it's a Gaussian, it extends beyond the cladding of the waveguide and actually goes into the other waveguide. And so as the photon propagates, there's a finite probability of finding the photon in the other waveguide. So photons actually tunnel from one waveguide to the other, just like you must have learned in your standard quantum mechanical courses about tunneling in finite step well, etc. You will see over here that photons also start to tunnel between waveguides which are kept in close proximity. Now over here, what I would like to specify is that there is a particular distance, and not by 2, where you can actually have the probability split between the two waveguides is equal. So there's a 50-50 chance over here that I can find the photon in waveguide 1 or waveguide number 2. And we're going to use this to create some interesting photon dynamics later. Now, before I tell you more details of the quantum walk, first of all, I would like to talk about what exactly are the uses of quantum walks. Why should I even study quantum walks in the first place? Why is it so interesting to me? So a lot of you must be interested in quantum computation. Well, quantum walks can be used to create universal quantum gates, and therefore they can be used to execute universal quantum computation at finite temperature. You don't have to go to super ultra cold atoms, etc. It is used in NMR, quantum information processing. It is used to study quantum transport, specifically photosynthesis. For example, in quantum biology, it's a very hot topic that plants are extremely efficient at transferring energy. Once they have done the process of photosynthesis, they can very extraordinarily efficient in transferring energy from their leaves to the other parts of the plant, etc. So how does that happen? That's a part of quantum transport. Spin excitation transfer in ferromagnets. You can optimize several quantum search algorithms using quantum walks. You can even simulate non-Hermitian quantum mechanics where there is non-unitary time evolution, etc. You can simulate topological effects. So a lot of quantum simulations can be done using quantum walks. Edge state transports, etc. Very hot topics in research. Those of you who must be interested. And the thing about quantum walks is that they are very ubiquitous. Their mathematical structure is so simple that it can be applied to several different types of physical systems, and therefore you can implement them using nuclear magnetic resonance, trapped neutral atoms, photons in fiber loops. You can use cascade of beam splitters, etc. You can do all sorts of things. So let's talk about discrete quantum walks. Now, like I said, in a continuous quantum, in a classical quantum walk, a quantum walker does a coin toss, and based on the outcome of the toss, he goes either to the left or the right. Well, we can do a similar thing in a discrete quantum walk, but instead of a classical coin toss, we're going to do a quantum coin toss, which is going to be splitting the probabilities at each step into two equal parts, which will be done by the Heidelberg operator. For those, many of you must be familiar with the Heidelberg operator, but those of you who are not, I must tell you, it's just think of this as a matrix which splits the probabilities into 50-50 for any given orthogonalized input vector. Now, what I want to be very emphasize over here is that you can see that over here, there's a single input state 1K, and the output is detected in detector number D4. But there are two different paths which we can take, depending on whether the first beam splitter over here is going to allow for transition or it's going to allow for reflection. And both transition and reflection have a 50-50 probability. So it's a Heidelberg operation. So you will see that both A and B result in the same detection in D4. But since it's a quantum walk, these paths A and B, these paths are going to interfere with each other. This is what is the interesting thing that happens in quantum walks. And they're going to interfere, and this interference is going to result into all sorts of interesting distributions that we will see later on. So let's talk a little bit about experimentation. I told you there's something called quantum walks. I told you that photons can tunnel between waveguides. I told you that you can do all sorts of you can mimic all sorts of quantum operations using this. But how do I physically even implement a quantum walk? So this paper published by Crespi in Nature, it's a very, very interesting implementation of a discrete quantum walk. So what you do is that you take borosilicate glass. This blue color material is a borosilicate glass. And you can use femtosecond laser etching, which means you use 3 femtosecond lasers orthogonal to each other, using which you can very precisely, very high precision, high versatility, you can create a region of high laser intensity. And because of some nonlinear absorption effects in the borosilicate glass, you can actually create regions in which that glass has permanently increased diffractive index. And therefore, you can actually create these something you could see these like pipelines. You see, these are actually waveguides because I've created regions which have a difference in the refractive medium, and that creates these waveguides. So you can use femtosecond laser etching, and you can create these waveguide lattices. Now, more details about this experiment is very interesting. It's like a landmark experiment. So over here, I see that there are different input states based on which waveguide I want to input into, and there can be different detections over here. Now, over here, you will see that there are a lot of waveguides which are coming close in physical proximity. These are directional couplers. These directional couplers have the exact amount of distance, which leads to a 50-50 split in the probability. Like I showed you in the beginning of the talk, you can actually, if you create at a sufficient distance, then there can be 50-50. This is actually implementing a Heidelberg operation. If a photon comes from here or from here, it has a 50-50 probability to either tunnel or to continue in the same waveguide. Now, there are also something called phase shifters. Because of the fact that I have absolute control over the refractive index, I can actually create regions of slightly higher refractive index. These regions of slightly higher refractive index increase the optical path length. And because I increase the optical path length, I actually can change the phase. And you will see over here that even a few micron, less than 1 micron, 0.2 microns of increase in optical path length is actually sufficient to implement a phase change of 3.14, let's say pi. And a phase change of pi is more than sufficient to do any sorts of experiment. So I have created a system where I have waveguides, I have created directional couplers which can do Heidelberg operation, and I have created phase shifters so that I can adjust the phase in each and every waveguide. Here you will see that different colors actually correspond to different phase shifts. These phase shifts are actually random. And so at each indexed waveguide, you have a random phase shift which creates static disorder in the medium. And we're going to use this static disorder to create some well-known wave effects and optical effects. We're going to reproduce them, but we're going to reproduce them in the quantum realm of things. So, okay, now I have my system. How actually do I go into the mathematical analysis? What results would I get? How do I go about the calculation? Suppose I insert 2 photons in the central waveguides A and B using parametric down conversion or some other techniques which are well known for producing single photons. How will I actually, how do I go and do this calculation? So first, let's talk about wave functions. Well, I can use a simple vector, a simple normalized vector to represent the number of photons in a particular waveguide. Let's say this is the waveguide number k. Then the kth index of this vector will be 1. All the others will be 0. As simple as that. I just need to take care of the normalization. And here, I want you to know that we are dealing with two different properties of the photon. We're dealing with the polarization of the photon, and we're also dealing with the position of the photon. So this vector will correspond to the position in the waveguide, which index. And I will have two particular polarizations, either horizontal or vertical, or I can have clockwise, anti-clockwise. It depends on your choice. But polarization of a photon is a quantum property of the photon, which can take essentially only two states. Let's say horizontal and vertical. And I'm going to use this polarization to actually implement some symmetries on the system. And we will see how symmetries in quantum mechanics affect quantum statistics, and they affect the propagations of these photons actually. So I told you that you can just do a tensor product between the polarization and the position. You have a wave function. Now you can do the spatial evolution by using a conditional shift operator. So our Hadamard is actually a quantum coin toss equivalent over here. Like you have a classical coin toss, heads and tails, you have a quantum coin toss in which 50-50% probabilities can change. Based on the output of the Hadamard operation, you actually have a projection of the operator. And based on the projection, either it can take 0 or 1. Based on one of these terms will hold. And then those terms will actually shift the probability from index number I to I plus 1. There will be a shift in probability over here. You can see that this projects to I minus 1, and this projects from I to I plus 1. This is how I study the spatial evolution. Now, to calculate the time evolution, I need to take care of the unitary operator, of course, and that will be given by the Hamiltonian of the system, of course. And this is an identity matrix of n dimensions, where n is the number of waveguides. We will just, this is just to take care of the dimensionality of the system. And of course, there is the spatial evolution, the shift operator, which is responsible for the shifting of the probabilities, the tunneling of the waveguide, the tunneling of the photons, the change of probability densities in the waveguide lattice. So what do I mean by waveguide lattice over here? Now I have kept a large number of waveguides next to each other. And I've already told you that they have the finite probability of tunneling. And therefore, when I inject a photon, it can tunnel to the left and the right, and then it can tunnel further, and it can keep on tunneling to several different, it can have all sorts of dynamics. So the final state of my output will just be given by applying the unitary operator t times to the initial state. If I want to study the evolution of two photons, because single photon dynamics gives you the exact evolution that you get in a classical light, so you don't really see any interesting quantum effects. But in order to see some interesting quantum effects, I need to study the evolution of two photons. Well, everything is the way I told you in single photons, only that for two photons, you have tensor multiplication. So you have photon number 1 over here, photon number 2, and this summation takes care over the possible states that it can take. So H and V correspond to the polarization, and psi A and psi B correspond to the spatial evolution. And therefore, by controlling, since I am creating the photons using some techniques, parametric down conversion, or whatever technique you want to use, I have control over the polarization of the photon. And using this polarization, I can create this initial wave function to be either symmetric or antisymmetric in nature. And this will lead to bosonic and fermionic statistics, as you will see. So to study the evolution of the two photons and to introduce random phase shifts to introduce static disorder into the system, I actually replaced the identity operator, identity matrix with this matrix, which is simply implementing random phases. 5 and 5, 2, these are all random numbers over here. This will create static disorder in the medium. And to study the unitary evolution, I simply do tensor products of the unitary operator for both the photons. And in order to calculate joint probability, what does joint probability mean? It's the probability of finding photon in the ith waveguide and the jth waveguide simultaneously. And you will see over here, these are just projections of the final wave function onto the possible outputs that it can take. It can be either horizontal, vertical, while being in the ith or the jth waveguide, and vice versa. So you take the projection of all the possible probabilities, and you use that to calculate the joint probability. So we have the mathematical structure clear. We have worked out the experiment, and this is the results that we get. Absolutely beautiful. First of all, let's talk about the order. When the system is ordered, I do not introduce random phase shifts. Everything is pretty much perfect. What I see is that when my initial wave function is symmetric in nature, when it is behaving bosonically, then initially I start with a particular, I suppose I inject 2 photons. And what I see with time is that this probability distribution actually spreads apart, and it creates these 2 ballistic lobes. So as photons propagate through the waveguide, they have a tendency to be at the 2 ends of the waveguide lattice. Similarly for fermions, also I see that there is 2 ballistic lobes, but these lobes are much more pronounced because this is an antisymmetric state. And fermionic states have a tendency to stay away from each other because fermions want to stay away from each other. They don't want to stay in the same state. This is because of their statistics. But as soon as I introduce static disorder in the medium, as soon as I do a random phase shift on each and every waveguide, what I observe is that, well, initially the bosons of the fermion, both the states start evolving, but slowly, with higher number of steps, with 8 discrete steps, they actually concentrate in the center. As you can see, fermions and bosons. Over here, the graph is very spread out. The joint probability distribution is very spread out. But here, it is highly concentrated. So why are photons concentrating in the center of the waveguide? Because we introduced static disorder. Well, we have reproduced a well-known effect in which is a general well-known effect in waves, which is known as Anderson localization. What happens in Anderson localization is whenever you have a large disorder in the medium, there is a lot of scattering. Because of this scattering, there are different waves, and all of these waves, there is so much interference that almost all the different waves interfere destructively except for a few. And therefore, it is possible to localize wave packets in certain spatial locations or certain regions in time, for our instance. And this is a general wave phenomena. It happens to, because it's based only on interference, So it happens with electromagnetic waves, acoustic waves. Where we've seen it happening over here with matter waves. It happens with spin waves. It happens with all sorts of waves. And over here, it's happening with the probability waves. It's happening with the matter waves of photons. And what we see over here is that photons are localizing. This is Anderson localization of photons in waveguide lattices. Very interesting. So this shows that our system is actually working, that our mathematics is consistent. It shows that our experiment is correct, and we are able to reproduce these well-known wave phenomena. Now, a word on symmetries again. If you look at the slight difference, this is bosonic and this is fermionic symmetry. You will see that there is still a little bit of difference in the fermionic symmetry, because they are fermions. Even though you have managed to produce localization, Anderson localization, even though photons are concentrated in the center of the waveguide, it still means that fermions still, they're not going to be in similar states. They're going to be different states. You see the slight gap. This is because in quantum mechanics, symmetries are so fundamental that you cannot defy symmetry. It's a rule that you simply cannot break. Now let's talk about continuous walks. So far, I was dealing with discrete time steps, and everything was very simple. It was on matrices, and our life was simple. But now I urge you to think in terms of a continuum. Suppose I keep waveguides in a lattice very close to each other, and suppose I inject a photon in the center. Well, what kind of distribution can I expect at the end of the waveguide? At what distance, actually? And what are the joint probability distributions going to look like now? So if you look at the Hamiltonian, for those of you who have some basic background in quantum optics, you know that this corresponds to the number of photons in a particular waveguide. This corresponds to the coupling that waveguide has with every other waveguide in the lattice. So if I'm talking about a particular waveguide index K, then how many number of photons are there in waveguide K, as well as how many photons tunnel from waveguide L, different waveguides L, into my waveguide K. This is the total energy in waveguide number K. And if I sum this energy for all the different waveguides, which is done by this summation, then I get the total energy of the system. And therefore, this is the Hamiltonian of the system. Now, this Hamiltonian is actually analytically very difficult to solve. As you can see, it's pretty big, pretty nasty. So we assume nearest neighbor coupling. where you get this coupling coefficient which comes through a classical calculation, and this nearest neighbor coupling simplifies this correlation coupling matrix to a tridiagonal matrix, because everyone is just dealing with their neighbor now. Nobody's dealing with a second neighbor. So in order to do the mathematical analysis, let's look at, well, we'll be dealing in the Heisenberg picture where the operators evolve with respect to time. And I can make a transformation of the Heisenberg picture because I want to study evolution in space. I want to study the evolution of probabilities as I go along the waveguide, not with time anymore. So I do a spatial evolution. When I work on the commutation relations, I actually get this equation. This is an equation of motion of the operator. Here, B dagger and A dagger are actually creation operators, which create probability densities in a particular waveguide. So these are creation operators. And this equation of motion is analytically solvable. And when you solve it, you get this kind of relation where we have a unitary matrix depending on the coupling between different waveguides. And this unity matrix is responsible for transferring probability densities from all the different L waveguides to the waveguide index as K. So then probabilities are coming from L to K. Everything is coming here. Now, for operators and measurements, well, you can just do measurement of number of photons using the number operator, which calculates the number of photons in a waveguide. And of course, our quality of interest is joint probability, which gives the probability of finding photons in index L and index K simultaneously, which can also be done by this is actually an advanced version of the number operator. But what is important is that you should focus on this graph, because this graph is going to help us to see the physics which is happening. Now, let's study single photon propagation. Oh, no. Let's try to first reproduce a well-known quantum effect, which is known as quantum Hong-Ou-Mandel effect. It was a landmark experiment done in 1987, and what we do in Hong-Ou-Mandel effect is that we only take two waveguides, which are very close to each other. Now I inject single photons into the waveguide. Now each photon can take two possible paths. Either it can continue in its parent waveguide, or it can tunnel to the other waveguide. And since both of these paths are going to interfere with each other, since they are matter waves, the paths corresponding to the output in different waveguides is actually going to destructively interfere. And what we will see is that the photons always exit in the same waveguide. So if I insert a state 1, 1, there's one photon in waveguide number 1 and the other in waveguide number 2. But the output is always 2, 0 or 0, 2. It's never going to be 1, 1, always. This is actually a quantum version of a classically well-studied effect known quantum Hong-Ou-Mandel effect. And what I want to specify over here is that we have actually generated very simple system, two waveguides, two photons. We've actually generated an entangled state. This is an entangled state. Both the photons are entangled now. And this is actually a bunching behavior because both the photons are trying to stick together. They're trying to stick together in one waveguide or the other waveguide. So this is a bunching behavior, and we will see this behavior when I increase the number of waveguides. So if I insert a single photon, and if I solve my equation of motion and I do my measurements of the operators, what I find is inserting a single photon over here, I actually get this kind of a probability distribution. It's absolutely gorgeous. You can see this is actually a Bessel function. There is one maximum of Bessel function is around here, and the other maximum is over here. This leads to these two ballistic lobes, these four lobes that you see in the joint probability distribution. But this is actually behavior same as classical light. If I were to insert a laser over here, I would see the same distribution. There is no quantum interference yet. In order to take care of quantum effects, I need to introduce two photons. So if I inject two photons into this system now, what I will see is now there's only bunching of photons. Either both the photons want to exit from here, or both the photons want to exit over here, just like you saw in quantum Hong-Ou-Mandel effect. They both wanted to exit from the same guide. Here, they're both trying to exit from this near similar waveguides. Either it goes to the left side or it goes to the right side. Because this is bunching behavior, both the photons are sticking together. Because all the paths which are corresponding to anti-bunching have destructively interfered here. This is a general wave phenomenon. This is a generalized version of Hong-Ou-Mandel effect. You will see that this probability density matrix, his joint probability density matrix is changed now. There's only two lobes instead of four. and either both of them want to come in 1010 or both of them want to come in 2020. The probabilities are very high. If I have an entangled state input, suppose I have this particular kind of an input where I can control phi, since I have control over my injected photons, I can create symmetric or anti-symmetric input states. Symmetric corresponding to phi equal to 0, anti-symmetric corresponding to phi equal to phi. And when I have a symmetric input, I see bunching of photons like I saw before. But when I have anti-symmetric input, this is anti-symmetric input, I see anti-bunching of photons. Now both the photons are trying to exit in different directions. If one goes to the left, the other one wants to go to the right. And we always observe this. Well, this was evident actually, because in an anti-symmetric situation, you have a fermionic input state. And since fermionic symmetry is anti-symmetry, fermionic states, they always want to be apart. They don't want to take the same states. So over here, there's an anti-bunching of elements. There is no classical equivalent to this. This is a purely quantum phenomena. It is coming from the quantum statistics of our input state. It is because of the fact that photons are bosons, and the fermionic symmetries are pushing the photons in different directions. Literally, the symmetry is pushing the photons to move in different directions in the waveguides. Now, a last word on two-dimensional lattices. You can also introduce two-dimensional lattices where you can have an X shape. Each of this corresponds to a waveguide, each circle. Then you imagine the waveguides going inside the plane of your screen. And when we can do inputs along 7 or 10 or 4 or 13 or 1, and we get all sorts of interesting dynamics. Suppose now I insert 2 photons in 7 and 10, across this and this waveguide. And what I see is that when I do a symmetric entangled state input, then I entangle 2 photons and the wave function is symmetric and I input those photons, I see that, well, there is bunching, but there is planar bunching now. So this is, so in this system, assume that this is one plane and this is the plane which is orthogonal to the other plane. And what you observe is that if I insert photons, symmetric photonic entangled input state into a particular plane, the photons tend to stay in that plane. They don't want to jump to the other plane. This is planar bunching. This is a higher dimensional version of Hong-Ou-Mandel effect, generalized version. This is planar bunching. And for anti-symmetric states, when I have anti-symmetry, when I insert them into this plane, they actually tend to go into the other plane. They want to jump into the other plane. This is planar anti-bunching. This is also what you expect in generalized Hong-Ou-Mandel effect, that photons are now jumping to the other plane. And I want you to observe these two graphs very carefully. These are actually complementary graphs. You see here the inner elements have high probabilities and the outer elements have 0 probabilities. But here the outer elements have very, very high probabilities and the inner elements are almost 0. So this graph is in some sense opposite to this graph, which was expected because the input states over here have exact opposite symmetries. Beautiful. So to summarize, we looked at what are quantum walks. We did some theoretical analysis about discrete and continuous quantum walks. I told you about how they can be experimentally implemented. And the publications are there in the references. I highly urge you to look at them. You can implement discrete and continuous quantum walks very comfortably these days. I told you how the influence of quantum symmetries has on the photon propagation in the waveguide lattices. And we have actually observed well-known quantum mechanical effects, well-known quantum optic effects, such as Anderson localization, Hong-Ou-Mandel effect, etc. In the waveguide lattice system, we have reproduced these well-known effects. And so we know that our mathematical analysis, we know that our experimental implementation, everything is very consistent over here. And so I can do quantum walks, I can play with them, and I can do all sorts of useful things, which I told you in the beginning of the talk. These are the references. I highly urge you to go through them. And I thank you for paying attention and thank you for your time. Yeah.
Okay, thanks, Valay, for such an excellent talk. So the talk is open for the questions. Yeah. Professor Panigrahi want to ask a question. Yeah, please.
Valay, excellent talk. Really liked your work.
Thank you, sir.
How difficult was it to design the, that optical resonators?
Optical resonators.
The experiment what you did.
Yes. Using femtosecond laser etching. Yes. So it's designed, I mean, it was designed in 2013, so it's a well-studied system by now. And I would say it's actually quite easy now because femtosecond laser etching, there are also a lot of people doing, so instead of femtosecond lasers, they're also using all sorts of high energy electrons on borosilicate glass, and even that creates, because of the birefringence of the borosilicate glass, it's actually non-linear absorption helps you to generate these regions of high refractive index. So I would say it's quite easy now for us to.
Okay. So there also, do you encounter paraxial, non-paraxial kind of domains?
Yes, I think so. There should be. I haven't read anything in the publications particularly because I was more focused on the theoretical side. But I wanted to give a experimental implementation so that people can see that this is actually being done out there in the real world. It's not just some mathematics that we worked out. Yeah.
Anyway, I'll be in touch with you about this. Thanks a lot. Very good talk. Enjoyed it.
Thank you, sir. Thank you.
Okay, so there is one question in chat box. So it is by Devdutt Sharma. So his question is, how can we detect bunching and anti-bunching either by measuring the probability or light intensity?
Okay, so in this case, you have to understand that probability and light intensity are actually the same thing. I want you to see that when you look at, suppose you're dealing with classical light, for example, then what do you observe? You observe the intensity of the light when you're dealing with lasers. Over here, what you're going to do is we're doing quantum mechanics, right? We need large ensembles. So when you set up your experiment, you do these input states, you input millions of photons. You do one experiment, you input 2 photons, you get output. Now there will be discrete clicks, in the I waveguide or at the K waveguide, and you will record that click. And you will have this input state multiple number of times. And what you will, after doing, let's say a few million times this experiment, you will get this probability distribution. And this is actually exactly equal to the joint probability distribution. When you will normalize that data set, you will get a joint probability distribution. So using single photon detectors for quantum walks, you're going to use single photon detectors at the end of each waveguide lattice. And this is how you do the measurement, actually. I hope that answers your question. Yeah.
Yeah, I hope he got his answer. So I want to ask you a question.
Sure.
You have mentioned about the tunneling within the waveguides.
Yes.
So as we know that in basic quantum mechanics, the tunneling happens when the barrier is higher than the energy of the particle. So what is the condition in this case? Is there any condition for the tunneling?
Yes. So the condition over here is that since your particle over here is a photon, and of course the wavelength of the photon corresponds to the energy, therefore you need to have your refractive index on your medium should be in such a manner that, first of all, both the waveguides are in close physical proximity, roughly like I told you, 40 times the wavelength of the photons, and corresponding to that wavelength, corresponding to that energy of the photon, then it will be able to tunnel. So if you use a similar waveguide lattice, but if you use a photon which has very low energy, then it may not be able to tunnel, you see. So you have to be careful about the physical distance of the waveguides, between the waveguides, and you have to take care of the wavelength, which means corresponding to the energy of the photon that you are input into the system. Right.
Okay, and the refractive index within the waveguide is real, or it can be complex also?
It can be complex also.
Okay.
Yes. So when you have so that's actually a very interesting question. When you have a complex refractive index, it's actually in the discrete walks, you do not have to worry about energy conservation because the number of photons entering into the system has to equal to the number of photons exiting into the system because it's a free space propagation, and you don't have to worry about energy conservation. Of course, energy will be conserved. We're doing physics. But when you're in the continuous quantum walks, because of the imaginary part of the refractive index, there can actually be an exponential damping because there is attenuation of light when it goes into the waveguides, right?
Yeah.
So in my talk, I had not mentioned this, but there is a very subtle calculation. You see that I have used A dagger as well as B dagger, 2 types of annihilation creation operators.
Yes.
The B dagger creation operators actually correspond to you have to do a transformation mathematically, and you have to be propagating within the frame of reference of the photon. When you do that, then you can ignore the energy dissipation of the photon traveling in the waveguide, because of course, as it travels in the waveguide, it is going to lose some energy, But over here, because we are at very small distances, and of course, like I said, you can choose your energy of the photon, you can ignore that dissipation, and mathematically you can do that by taking care of the transformation of the frame of reference in the photon. You can change your operator. So yeah, that helps.
Okay, thanks. So this is the end of this morning session. So I want to thank all the speakers and participants. So we will be back around 3 p.m. for the afternoon session. Okay, thank you very much.
Thank you.